Here's a number I want you to sit with for a second: 700 billion. That's how many events Netflix processes every single day. Not requests, not page loads. Events: every play, pause, seek, buffer stall, quality change, subtitle toggle, and recommendation click that happens across 220 million subscribers, all day, every day. Uber processes over 1 million events per second at peak. LinkedIn ingests more than 1 trillion messages per day through its internal messaging infrastructure. These aren't just big numbers for the sake of sounding impressive. They represent a fundamental architectural choice that makes those systems possible. That choice is event-driven architecture. If you've ever wondered why your Netflix keeps playing smoothly even when half the internet is also watching on a Friday night, or why your Uber ride shows up even though thousands of other rides are happening in the same city at the same time, a big part of the answer is events. Today, I want to unpack what event-driven architecture actually means, why it exists, how Kafka made it mainstream, and the real patterns you'll use when you build systems this way. Including the trade-offs, because there are real ones, I'm Alex. This is Bot Thoughts by AmtocSoft. Let's start with the architecture most of us learned first: request response. You have a service, a client calls it. The service does something, then responds. The client waits. Simple, direct, easy to reason about. This works beautifully at small scale. Your monolith, your startup, your side project, request response is fine. It's synchronous, it's predictable, and the debugging story is good. Something fails, and you can usually trace exactly what happened. But synchronous systems have a fundamental problem at scale: tight coupling. If service A calls service B, and service B calls service C, then every request is a chain. Service A can't finish until B finishes. B can't finish until C finishes. Every link in that chain is a failure point. Every latency spike ripples upstream. Now imagine Netflix's recommendation engine. To generate your home screen, it might need to consult your watch history, your friend activity, trending content, your device capabilities, your subscription tier, and a personalization model, potentially 6 or 7 services. If they're all synchronous calls, your home screen load time is the sum of all of them. If anyone is slow or unavailable, your home screen fails. At 200 million users, that tight coupling becomes a liability. You can't have a slow machine learning service taking down the browse experience. You can't have a payment service outage preventing anyone from playing videos. The architectural response to this is decoupling, and the most powerful form of decoupling at scale is events. Before we go further, let's make sure we're using words correctly, because event gets used loosely and that creates confusion. An event is a record of something that already happened. It's a fact about the past. User paused video at timestamp 2314. Order was placed. Payment was received. Events are immutable. You don't go back and change the fact that something happened. You might publish a new event that corrects it, but the original stands. Compare that to a command. A command is a request for something to happen in the future. Process this payment. Send this notification. Commands can be rejected. Events can't, they already occurred. And a query is a request for information. What's the current balance in this account? No side effects, just a read. Event-driven architecture is specifically about events, those immutable records of facts. When something happens in one part of your system, it publishes an event. Other parts of your system that care about that event subscribe to it and react. Crucially, the publisher doesn't know or care who's listening. This is the key mental model shift. In request response, the caller knows and depends on the callie. In event-driven architecture, the publisher doesn't know its consumers. The event goes onto a bus or a log, and whoever needs it reads it. The publisher keeps moving. That decoupling is what makes event-driven systems scale. Netflix's playback service doesn't wait for the analytics service to record your play event. It publishes the event and continues. Analytics consumes it asynchronously, in its own time, at its own pace. For a long time, if you wanted a message queue, you had options. RabbitMQ was popular. Amazon SQS. ActiveMQ. These are traditional message brokers. They pass messages from producers to consumers and delete them once they're consumed. Works great for task queues, job processing, fire and forget notifications. Kafka took a fundamentally different approach, and that difference is why it became the backbone of event-driven architecture at scale. The core insight is this: Kafka is a distributed log, not a message queue. When you publish an event to Kafka, it's appended to a log. It stays there. It isn't deleted when a consumer reads it. Consumers track their position in the log, their offset, and can read from wherever they left off. They can also, if needed, rewind and read historical events. Why does this matter? A few reasons. First, durability. In a traditional message queue, if no consumer is running when a message arrives, the message might be lost. In Kafka, the message is persisted to disk, replicated across brokers, and sits there waiting until a consumer reads it, whether that's milliseconds or days later. Second, multiple consumers independently. With a traditional queue, each message goes to one consumer. With Kafka, multiple independent consumers, Kafka calls them consumer groups, can all read the same events, each maintaining their own position in the log. Netflix's analytics team and their real-time alerting system and their ML training pipeline can all read the same stream of play events, each doing different things with them, without affecting each other. Third, replay. If you deploy a new service that needs to process the last 30 days of events, it just reads from the beginning of the log. You don't need to reconstruct historical state from a database dump. The events are right there. Kafka partitions logs across multiple brokers for horizontal scale, uses replication for fault tolerance, and handles millions of events per second per cluster. It's not the only tool in this space. AWS Kinesis, Google PubSub, and Apache Pulsar are worth knowing. But Kafka is the reference implementation that most event-driven architectures are designed around. Knowing what event-driven architecture is conceptually is one thing. Knowing how to actually build reliable systems with it is another. There are 3 patterns worth knowing deeply. The first is the outbox pattern. Here's the problem it solves. You have a service that needs to update a database and publish an event atomically. The payment service marks an order as paid and must emit a payment received event. But what if the database commit succeeds and the Kafka publish fails? Your database says paid, but downstream services never heard about it. The outbox pattern solves this by writing the event to an outbox table in your database in the same transaction as your business data update. A separate process reads from the outbox table and publishes to Kafka. Because the outbox write is part of the same database transaction, it's atomic. The event either makes it into the outbox with the data update, or neither happens. This is one of those patterns that sounds obvious once you hear it, but took the industry a while to standardize. The second is event sourcing. Instead of storing the current state of your entities in a database, you store the sequence of events that produced that state. An account doesn't have a balance column. It has a list of deposit and withdrawal events, and you derive the balance by replaying them. This sounds strange until you realize what you get: a complete audit trail, the ability to reconstruct state at any point in time, and a natural event stream for downstream consumers. It comes with real complexity. Querying event source systems is harder, but for domains where auditability and historical reconstruction matter, it's powerful. The third is the saga pattern, which solves one of the hardest problems in distributed systems: transactions that span multiple services. In a monolith, you have database transactions. In a distributed system, you can't hold a lock across 3 services. The saga pattern models a multi-step business transaction as a sequence of local transactions, each with a compensating transaction that undoes it if something later in the sequence fails. If your order service succeeds but your inventory service fails, the saga triggers a compensation, cancels the order, notifies the customer. Each step publishes events. The saga coordinator reacts. It's more complex than a database transaction, but it's what actually works at scale. Event-driven architecture is not a free lunch. Here are the trade-offs I want you to understand before you adopt it. Eventual consistency is the big one. In a synchronous system, when your write returns successfully, all readers will see the update. In an event-driven system, there's a delay, potentially milliseconds, potentially longer, between when an event is published and when all consumers have processed it. Your UI might show a stale state briefly. Your analytics might lag. This is usually acceptable, but it requires you to design your product and your user experience with eventual consistency in mind. Debugging is harder. In a synchronous call stack, you have a single trace. In an event-driven system, a business transaction might involve 5 services, each reacting asynchronously to events published by the last. Distributed tracing, passing a correlation ID through every event, is essential, not optional. Without it, you're flying blind. At least once delivery is a fundamental guarantee in Kafka. Kafka guarantees that events are delivered at least once to consumers, but not exactly once by default. This means your consumers must be idempotent, capable of handling the same event twice without double applying its effects. If a payment event is consumed twice, the account should still only be charged once. Designing for idempotency is a discipline that takes practice. Here's my honest take: start synchronous. If you're building a new product, a new service, even a new startup, don't build event-driven from day one unless you have a specific, concrete reason to. Event-driven architecture adds real complexity. You now have Kafka to operate, schemas to version, consumer offsets to manage, and idempotency to think about. For a team of 3 building an early-stage product, that overhead is probably not worth it. The pain points that signal you're ready for events. You're seeing cascading failures where one slow service takes others down. You have multiple services that need to react to the same business events. Your analytics, your notifications, your audit log all care when an order is placed. You need to decouple deployment cycles between teams. Or your message volume is high enough that synchronous processing creates a latency bottleneck. When those pain points appear, introduce events incrementally. Start with one event stream. Get operational experience with Kafka. Learn what idempotency means in your domain, then expand. The pattern that tends to work well is the strangler fig. Keep your synchronous core and introduce events at the boundaries, between services, at the edges of your domain. You don't have to rewrite everything to benefit. 700 billion events per day. That number sounds like infrastructure magic, but it's the result of a clear architectural decision. Decouple your system by making it event-driven. Producers publish facts. Consumers react asynchronously. Nobody waits. Kafka made this practical by treating the event stream as a durable, replayable log rather than a traditional message queue. The patterns outbox for reliable publishing, event sourcing for audit-complete state, sagas for distributed transactions, are the engineering toolbox you reach for when building on top of that foundation. The trade-offs are real: eventual consistency, debugging complexity, idempotency requirements. But at the scale where it matters, these are better problems to have than cascading failures and tightly coupled services that can't evolve independently. The full deep dive on event-driven architecture, with code examples for the outbox pattern and a Kafka setup walkthrough, is in the show notes. This is Bot Thoughts by AmtocSoft. I'm Alex. If this was useful, subscribe wherever you get your podcasts. See you in the next one.